Let's take a look at a couple of problems that involve energy. So we're starting with free fall Eddie. He's in an elevator. Okay, so he's going up, so his height is changing. He has a weight, and we know how high each floor is. So we want to find his potential energy on the 5th floor. So we're looking for EG, and that equation is his mass times G times H. Well, we learned earlier that M times G equals weight. So his weight we have already 750 newtons. And he's going up 5 floors times 4 meters per floor. So his gravitational potential energy compared to the ground floor is going to be 15,000 joules. Now, unfortunately for poor Freddy, the cable snaps. And what we're looking for is the kinetic energy right before hitting the ground. Well, if he's falling, he's essentially free falling, so he's accelerating. His initial velocity and we want to find is 0, and we want to find out his final velocity. Just before he hits the ground, his gravitational potential energy is 0. Before the cable snapped, the kinetic energy was 0. So what happens to all that gravitational potential energy? Well, it gets converted to kinetic. So we can say that gravitational potential energy equals kinetic energy. We found out what the gravitational potential energy is, 15,000 joules. So what that means is he has 15,000 joules of kinetic energy just before he hits the ground. How does that help us? Well, that helps in solving part C, because in part C we want to find out, okay, great, how fast is he going just before he hits the ground? Well, kinetic energy involves velocity, so we can use our knowledge of kinetic energy and the equation to find out his velocity. So kinetic energy, again, is 1/2 mass times velocity squared. So we have 15,000 joules is his kinetic energy. 1/2 mass. Well, we don't know his mass because they gave us his weight. But we know from our equation that mass is his weight divided by 9.81 newtons per kilogram, gravitational field strength, times v squared. We're looking for velocity, so we never know everything except velocity, so now all we have to do is solve for it. Do the algebra, hit the right buttons on our calculator, and what we find his velocity just before he hits the ground is 19.8 meters per second. And if I look back up to my numbers, I have 3 sig figs, 3 sig figs, so my answer can have 3 sig figs. So there we go. If I look at the next problem, I have a car being loaded onto a truck. I have a ramp length of 6 meters, and I have a car mass of 1,500 kilograms. So I have the mass this time. I'm looking for the increase in potential energy. Well, how do I do this? First thing I would probably do is draw a diagram. So there's my ramp. Here's my car. It's 6 meters long, and I have a 20-degree angle. So here's my height. Height is the side opposite my angle. So if I want to find it, it's going to be 6 meters times the sine of 20 degrees. And what I get for that is 2.05 meters. So now I can put it in the gravitational potential energy equation. My mass is 1,500 kilograms. G is 9.81 newtons per kilogram, and my height is 2.05 meters. So my gravitational potential energy is 30,197 joules. All right, if I wanted to be picky, I see it was 4 sig figs, so my answer can have 3 sig figs. So gravitational potential energy is 30,200 joules. All right, now I'm looking at some dissipated energy. It takes 90,000 joules, it says, to get the car to the top of the ramp. And gravitational potential energy the car had when it got to the top of the ramp is only 30,000 joules. So what happened to the other? That's what must be lost. So total energy, in this case, is going to be gravitational potential energy plus dissipated energy. Okay, the total amount of energy that's going into the system to lift the car up is 90,000 joules. We figured out it's 30,200 that the car possesses when it gets up there. So our dissipated energy. Do the math, we get 59,800 joules is dissipated. So there are some examples of how to set up and solve energy problems, definitions of the different types of energy we'll be working with in this unit.